I thought that we will do a recap on Bayesian network inference, because when I looked at your assignment 5, most of you got the condition independences right. There were a couple of tricky ones where people made mistakes. Most of you got the first question, which was the joint probability distribution, but I think more than half of you missed the last question, which was the conditional probability distribution. Which is not surprising, because the last time we did Bayesian networks, it became a bit too heavy for us, and I think it makes sense for us to go back and redo some of that part. I'm not going to redo the deseparation part, but I think this part of variable elimination and so on is extremely important, so we'll run through the example. Not run, we'll slowly go through different steps of an example. And what I would like you to do is, especially if you got your last question wrong, okay, in the previous assignment, please redo that for yourself, for your sake, redo that question and get the right answer. And the right answer is 0.1683 or something like that, 0.1663. Send it to you in an email. So hopefully after today's class, when you go back and redo it, you will get it. But you should get it, because otherwise you will have a harder time in at least one exam question and in the next assignment, which we'll talk about.
Can you post the solutions to that as well?
I will. Almost everybody got the second last question right. The question that you don't know the answer to is the last question. Everything else you can see on your catalyst anyway. But I'll post it. Okay. So let's get started. So here's a quick recap of Bayesian networks. I think you sort of all remember this, hopefully, because you did the assignment, but still let's go through it. So this is the executive summary. We realize that we can answer any query if we have a full joint distribution, but a full joint distribution is so huge that we neither have memory nor any time to process it. So we need to compactify our representation, our model, such that we can answer the questions meaningfully. And the way we are going to do this is by using a directed graphical model called Bayesian networks. This is not the only way to do it, there are others, but the high-level concepts that you learn in Bayesian networks are going to stick with you for a long time in different scenarios. So a graph is a graph, but we have to give it some semantics. And the semantics that we gave the graph is that, first of all, the joint distribution can be represented as a product of factors, where the factors are the conditional distribution for each node given its parents. Second, any graph structure would naturally encode some conditional independence assumptions, and those conditional independence assumptions are, we went through all of them. The easy ones were that every node is conditionally independent of all non-descendants given its parents. Every node is conditionally independent of all nodes given its Markov blanket, and Markov blanket is my children, my parents, and the other parents of my children. And then, in a general sense, if we have to figure out a general condition independence, then the rule is called deseparation, and we went through the rule for doing the general condition independence as well. Slightly subtle, people make mistakes once in a while, but the high-level concepts hopefully you have got. And in that context, I posted a video of Daphne Kohler, who is sort of the leading expert in the world on probabilistic graphical models. She's also co-author of the sort of fattest book I have seen on this subject, and it's really, really exhaustive and extensive. And her lecture on, again, similar concepts on computing condition independences in a Bayesian network is extremely clear. So after the class, hopefully you got a chance to look at that 15 minutes of lecture. But if you haven't, and if you still think that you are not very clear about deseparation, please go and look at that video. It's really clear, and it will make your life much easier. Now, towards the very end, we did inference. And that is where we are going to start from. We're going to start with exact inference. And the question of inference is the following. So, it's a knowledge representation framework, Bayesian networks. We have some knowledge about how the world operates. And we want to be able to ask questions. We have seen some observations. We want to ask questions based on our knowledge base. That's the high-level inference task. And in that context, we want to compute two kinds of probabilities. One is called the marginal probability, and the second is called the conditional probability. A marginal probability just means what is the probability based on this Bayesian network that z, a variable, has a certain value, or z, a set of variables, have a certain set of values. So, without knowing any new information about anything, I am just asking what is the marginal probability of a certain variable or a certain group of variables having a certain group of values. Okay? And the second is called the conditional distribution, a condition probability, which is much more common and much more useful in practice, where the idea is that I have seen something already. I have seen some evidence encoded in E. So I have seen that certain variable is true, another variable is false, and this, that, and the other. And now, based on what I have seen so far, I want to be able to compute some query variables. The query variables are called Z in this lecture, and evidence variables are called E. And there are also other variables which are neither query variables nor evidence variables, and for the context of this particular discussion, they are hidden. So we don't care about them, but we will need to do something about them because they are in the network. And the main idea is that because we have this network topology, we want to organize our computations using the topology. Now this is very important because we can ask multiple types of questions, and each question has a different practical interpretation. So I could ask, what is the probability that John is going to call if there is earthquake? Suppose I want to figure out that John is actually useful, so I have this Bayesian network. So let me ask, is John really meaningful for me? Is he going to call when there is earthquake or not? Similarly, so that's causal reasoning. The other reasoning is evidential reasoning, where I say, okay, I know that John has called. Now, what is the probability that actually burglary has happened, and I need to be worried about it? So that's the causal reasoning. What is the probability of the cause given I have seen some observation? There are other kinds of questions which are intercausal. For example, I have one observation that alarm went off, but I have multiple causes that alarm could have gone off through earthquake, alarm could have gone off through burglary. So I want to compare the various probabilities between, is it more likely that earthquake happened, or is it more likely that burglary happened? In fact, more interestingly, suppose I know the value of alarm and I know the value of earthquake. Then I could ask the question, given that I know earthquake and alarm, what is the probability of burglary? So this is sort of a non-trivial kind of a question, but this is very interesting because it's sort of saying that I have multiple causes. Now I know the value of one cause. Does it make the probability of other causes go up or go down, or what happens? So for example, if I knew earthquake happened and I knew alarm went off, then that will give me a belief that most likely burglary did not happen, so let me not worry about that. So this is intercausal reasoning. But any kind of reasoning that we may need given our Bayesian network, the algorithm to compute it is going to stay exactly the same. So that is the power. There is one single or one set of algorithms which do inference in Bayesian networks, and you can use it for evidential reasoning, causal reasoning, intercausal reasoning, any kind of. Now we are going to focus on this algorithm called variable elimination. There are other exact inference algorithms which we will not study in this class. The reason we will study variable elimination is that A, it's easy, and B, it's easy. Yeah, that's the reason. Okay. So you can think of variable elimination, and this is where I think we should all come in. So variable elimination will be organized, the algorithm will be organized by factors. A factor is a function from some set of variables into a specific value. This notion of factor is actually much more general than Bayesian networks. So tomorrow, if you go and you have to study some new network called Markov network, or conditional random field, or all of these terms that we, dynamic Bayesian network, there are many networks. Okay. Chain graphs. Don't be worried. The main thing is you have to identify what are the factors. Once you identify the factors, you have solved half your problem. Okay. Everything in all of these graphs happens through factors. The factors mean differently, they get normalized differently, and so on, but essentially they are factors. So let's think about it. So conditional probability table is a factor, right? It's saying probability A given EB is really a function of AEB going to some value between 0 and 1. Now notice the way I defined the factor, the value doesn't have to be between 0 and 1, but for conditional probability tables, they are between 0 and 1. When you do Markov networks, they will be from 0 to infinity. Okay. So what variable elimination does is, by, as its name suggests, it eliminates variables. one at a time, and keeps computing factors until we are left with only the query variable, and now we have got our answer. And how do we eliminate variables? Very simple. We collect all the factors that refer to that variable. So suppose I want to eliminate A. So I look at this factor, this has A in it, yes, I will take that. I look at this factor, this has A in it, I will take that. I look at another factor, it doesn't have A in it, I don't care. So I collect all the factors which are function of A, and then I join all the factors and sum out the influence of the variable. And we will see an example step by step to get a sense of it. And because we know that joint distribution is just a product, so life gets easy. So Bayesian network semantics really helps us in performing this. So let's do one step at a time. The very first step in all variable elimination problems is to write your probability that you want to compute in terms of the joint distribution. So if I want to compute the marginal probability of J, I will say that it depends on the joint distribution J, M, A, B, E, and I have to sum out M, A, B, E. On the other hand, if I have to compute the marginal of J and not M, then I will say that I have to sum over A, B, E, exactly the same term, except that J is known, M is known, A, B, E are not known, so both of those values will happen, and I'm going to be summing up. In the previous set of lectures, I was not distinguishing between a variable and a value. But in this case, for now at least, I want to make sure that you get the subtlety right. So here, it's a joint distribution, but here A will take all possible values, B will take all possible values, but M is not going to take all possible values, M is only going to take the value false. We know this. This is given to us, this is what we want to compute. So far so good? Now let's talk about conditional probabilities. Suppose I want to compute conditional probabilities. This was for marginal, fix the query variables, sum over unknown variables. Now the conditional probabilities, fix the query variables as before. Now we also have evidence variables. So fix the evidence variables. It is known to us, so we don't have to sum over them. Sum over unknown variables as before. Moreover, add a normalization constant. Okay? And some of you were still confused about normalization, so let's make sure that we understand this. So suppose I want to compute probability of burglary given that John called and Mary called. So this is just for your derivation. So we know that any conditional probability can be written as the joint probability divided by the probability of evidence. Now if I wanted, I could compute this separately and this separately. It's nothing wrong with it. But we are saving some time, so the way we will do this is that we will say that this is proportional to B probability of B, J, M. And the reason is that J and M are known. And B is the one that is varying, so burglary can be true or false. That for burglary true, we will have BJM divided by JM. For burglary false, we will have not BJM divided by JM. So for both of these cases, we are dividing by the same value. So why worry about it? Let's get rid of this value and say it's a constant and say that this probability is equal to alpha times probability of BJM. Now where will this alpha come from? Well, the alpha will come from the fact that probability B given Jm plus probability not B given Jm should be 1. So if you don't compute this denominator, this we will have to normalize this alpha so that this probability and this probability sum to 1. So it's just the ratio has to be maintained. And now probability Bjm is nothing but, using the same idea, sum over AE joint probability distribution. So essentially what we have done is that we have taken either the marginal or the conditional and rewritten it as sum over some variables, a joint probability distribution with a possible normalization constant. Yes?
Cost of computing of BJM, but at the same time
we will compute both of these, because typically what happens that whenever you ask for a query, you say what is the probability of burglary given John and Mary called, you want to return the full distribution as opposed to just one value, typically. So if suppose you want to ask what is the probability of a heart rate given the person has high fever and low blood pressure, whatever. So then what you would like to give is that you will say, well, the person may have low heart rate with this probability, medium heart rate with this probability, high heart rate with this probability. You will rarely say that I just want to have that one value. And even if you want to have one value, the variable elimination algorithm will work just fine if you are computing k at the same time. So it will be exactly the same computation. Okay. Step 2. So step 2 is rewrite the joint probability distribution, joint probability using Bayesian network factors. So I think everybody but 2 got this question right in the assignment. So I think you already know this. If I give you J, M, A, B, E, you can easily write it as P, B, P, E, P, A given B, E, J given A, M given. You just go through the Bayesian network topology and do product of a node given its pairs. So far so good. And now because this is sum over some variables, it will be sum over the same variables. Now comes the variable elimination part. So up until now we are just rewriting the probability that we want to compute. Now let us talk about the algorithm. So the algorithm does the following. It chooses a variable order and eliminates one variable at a time and uses all the factors that are relevant to that variable when it is eliminating. So for example, suppose this is what we want to compute. Sum over MABE, PB, PE, PA given BE, J given A, M given A. Suppose my order is MAEB. So the first variable I want to eliminate is M. So what are all the factors that will be necessary for eliminating M? Well, all the factors that have M in it. So what are the factors that have M in it? Only one, M given A. So this is that part. Now this will be a function of A, right? Because this was a factor of M and A, I eliminated M. So now it's a function of A. Next is that I want to eliminate A. So let's see what are the factors that have A in it. So PA given BE has A in it, PJ given A has A in it, and this new factor that I have created after eliminating M has A in it. So I will take all of their products and sum A out. Similarly, I will sum E out. So this is a function of E because of this E here, PA given BE. So I will multiply it with PE, sum E out, and then eventually I will multiply with B and sum B out. Now I could choose another order. So suppose this is my example, a different example, sum over AE. If I choose A first and then E later, then this is what I will get. I will collect everything with A in it first, sum out A, and then multiply with PE, sum out E, and B doesn't appear. If however I choose EA, then I will compute everything with E in it first. So these will be these product of PE, PA given BE, and then sum out A, which will be product of these two, and then B. Both of these are fine. Any order is fine. You have to pick one order. Now, a good order is better than a bad order. I mean, the order actually sometimes a bad order can make your inference exponential, and a good order can make it linear. This can happen. But conceptually speaking, any order is fine. Any confusions at this stage? Let's go through an example to make sure that we understood variable elimination. So our example would be, surprise, surprise, burglars and earthquakes. I hope nobody starts an alarm company after this course. Too much alarm business. So this was a Bayesian network. And suppose we want to compute this particular term. Sum over MABE, PB, PE, PA given BE, PJ given A, M given A. Basically, you want to compute the marginal probability that John will call. So one step at a time. Sum over MP, M given A is what? What am I saying? I am saying for A true, I will add 0.7 and 0.3. And for A false, I will add 0.01 and 0.99. So this is a sort of a silly computation. We really don't need to do this, but even if we did this, we will get 1, 1. So we will see why this can be cut off, but basically we can cut this off because this is going to be 1. Now let's do the more interesting computation. So this is the next computation. We have to do sum over A, PA given BE times PJ given A. J is known to us. J is that John called. So what is this? What variables will this be a function of?
Can you remind me how to read these tables? I'm
Oh, sure. So this says that probability that John is going to call given that alarm is true is 0.9, and probability that John is calling given the alarm is false is 0.05.
In parentheses is the converse?
Yeah, the John will not call given alarm is true is 0.1. Each row should sum to 1. So what is this a function of? B and E, right? Because this is a function of A, B and E, this is a function of A because J is known to us, and we are summing out A, so this is going to be a function of B and E. Let's create this function. Suppose E and B are both true, okay? Then which numbers am I going to multiply and what am I going to add? E and B are both true. One at a time. What will be the first term? 0.95 times 0.9. And then plus, because we are summing out A. So plus. Now which value of A are we going to look at now? False. Now alarm hasn't happened. So which term will we be taking from here? 0.05, because alarm hasn't happened but E and B are true. And which term we are going to take from here? 0.1, because alarm hasn't happened. Sorry, 0.05. Okay, so this is wrong. I made a mistake. Forget. You guys got it right. Let's make it on the board.
That's right.
Is it right?
That's right.
No.
No, I don't think it's.
0.05 to 0.05.
Yes, exactly.
Close. Wow, I'm so glad I've never done that.
I don't have a pen. Sorry. But you got this, right? So 0.95 times 0.9 plus 0.05 times 0.05. Let's do the next one. Suppose E is true and B is false. E is true, B is false. First term would be 0.29 multiplied by 0.9. And second term would be no alarm given E true, B false, 0.71. And no alarm means 0.05.
A is true.
So before the summation, A is going to be true. After the summation, A is going to be false, and this should be 0.05. Do we need to do more, or you guys got this? All of these 0.01 should be 0.1 should be 0.05. Okay. So we got this. So let us assume these numbers are right. All of these are not right because I made a mistake. But let's keep. So now this is my F2. This is a function of E and B, and it has a value for each E and B. Now let's go forward. So now I substitute this by F2BE, and now I have to sum out E. This will be a function of simple. So I take, let's see. So for B true, what am I going to multiply? So for B true, we are at B true, and so let's start with E true. So E true and B true is 0.86 and 0.002 plus. Now I have E false, B is still true. 0.852 times 0.998. You get a similar next one. So now you got F3, and now you got F3, then you can similarly do this and this. You can compute your final result. This is the algorithm. Yes?
How did you eliminate F1? Meaning
Yeah, we will get there. So we talked about computing alpha. So suppose I want to compute this alpha. So B given Jn, I have written it as equal to alpha P Bjn. So you compute P Bjn and you compute P not Bjn. And you say that I'm going to normalize this combination so that the probability sum to 1. So I multiply them with such an alpha such that they sum to 1, which is equal to that alpha will be 1 over P Bjm plus P not Bjm. Yeah, exactly, same thing. It is. You can do. So you will have to do two variable eliminations independently. That's wasteful. So that's why you have the. So now any other questions on variable elimination? Does it still sound like a hard algorithm? You can make mistakes. But as an algorithm.
yes, it does.
Really?
It's
I couldn't begin to implement this given a Bayesian network, but.
Okay, so that will be your assignment, but we'll talk about that.
It seems very error prone to do by hand.
Yes, and that is
Probably
why.
so many people missed it.
Exactly. So we can make mistakes. I made this slides last night watching a cricket match, and so you can see that that's not a good idea.
Somebody should write a program that does this.
And 20,000 people have written it. So, and after the end of the class, you'll have 42 more. So, I'm kidding, by the way. Your last assignment is going to be extremely easy. But yes, Abhishek. Good. Yes.
Can you walk through again how the F1 was eliminated?
Yes. Getting there. Yes.
So why did you say like if you choose a different order, it can go from become exponential suddenly?
Because some factors may become really huge if you choose wrong order. You might keep adding variables and not eliminating money.
So if you follow the tree approach,
The Bayesian network, right? Bayesian network may not be a tree, and the reason is that there will be multiple paths to the same node. If there aren't any multiple paths to the same node, it is called a polytree, and in that case, the complexity is a polynomial probably. But if you have a polytree, then it can become exponential, and we will do a proof to show that it's actually NP hard. I am going to do a proof today. But let's just do the notes. So each operation is a simple multiplication of factors summing out a variable. Complexity is not determined by the number of variables. We are eliminating one variable at a time. So complexity is really linear in the number of variables in that sense. The question is how bad is each multiplication? And if my factor is a factor of many variables, then my complexity is exponential in that size. So if my so in this example, we were multiplying, I think, 3 variables. So the complexity will depend on 3, not 5. So it's exponential in the largest factor that I'm going to be eliminating. Optimal elimination orderings are NP hard, which is not surprising because the problem is by definition NP hard. So if you could come up with optimal elimination orderings, then for many problems at least it would become less than NP hard, and that will be not common. There, however, and so there is a correlation between CSPs and Bayesian networks, and the correlation is or satisfiability in Bayesian networks. So there is an equivalent algorithm for variable elimination in CSPs called bucket elimination. We didn't study it, but what is the point? The point in CSPs is that I want to have only one assignment. So we are talking about ones and zeros only, and everything is deterministic. Here we are talking about the probability. So it's a harder problem. Bayesian networks is a harder problem, but the ideas still stay. So we talked about cycle cut sets in CSPs. We will have cycle cut sets in Bayesian networks. People have studied probabilistic cycle cut sets. Which variables do I first set so that my structure becomes polynomial and things like that. Those ideas, there's a huge commonality between those. So similarly, as we had in CSPs, for tree-structured CSPs, we had polynomial algorithms. Similarly, for polytree structured Bayesian networks, we have polynomial algorithms. So there are tractable subclasses of Bayesian networks which are where inference is polynomial. Right. You may ask, how do I choose my variable order? Right. And there are many heuristics that people have studied for choosing variable order for elimination. We will not get into those heuristics. But I'll tell you the simplest heuristic possible. Choose a variable which results in the smallest factor. It's not a very good heuristic, but it's better than random variable heuristic. There's one other thing that I would like to tell you when you implement this in practice. See, you are multiplying lots of probabilities. When you are multiplying lots of probabilities, what could happen? Underflow. This is not that bad a situation for variable elimination, but once you get into hidden Markov models, which we will unfortunately not cover in the course, but then you are multiplying lots of probabilities over long periods of time, they will all just go down to 0 very quickly. So what do people typically do? Take logs and add. So those are ideas you need to just remember. To answer Sameem's question, why is sum over m, p, m given a1
can do it and say.
And then probability.
M given A is M.
No, m given A is not m,
No, it's not.
but we are summing over m.
It's
Well, that's
the
weird.
parent.
It's like probability of M and not.
It's like summation probability of something of all possible alternatives is what? 1.
Right.
So we could eliminate this right away, right? It's sum over m probability of m, given something. Now the question is, how can we identify this ahead of time so that we don't even consider it? And there's a very simple theorem which says that m is irrelevant to the computation if it's a descendant of the query and evidence. Query and evidence. So in other words, unless a variable is either an ancestor of the query or an ancestor of the evidence, it is irrelevant. So in this case, probability of John calls Mary is irrelevant because it is not an ancestor of John calls. And you should think about the intuition. The intuition is actually very simple. We are computing, so probability of John calls depends on, we will start from here, we'll say earthquake might have happened, burglary might have happened, alarm might have happened. Once alarm happened, then Mary called is independent and John calls is independent. So the descendants don't matter. Now if you're conditioning on the descendant, then life is different. But here you are just computing the marginal probability. So what is happening below my query and evidence variables is not important. What is happening on the side is not important. What is happening above me is important because that is where the information is flowing from. Let's do the proof, since now you guys are experts in Bayesian networks. This is for the theoretically minded. I won't test you on the exam, but it's not hard, so you might just learn it. It's pretty awesome actually. So the claim is the following: Bayesian network inference is NP hard. Now do you know how do we tell that something is NP hard? What is the basic strategy?
Use an NP hard to this.
We take an NP complete problem and reduce it into this problem. We have studied one NP complete problem, that is SAT, right? 3 CNF. So let us convert CNF into Bayesian network. So what we have to do, we have to create such a Bayesian network so that if we can solve the Bayesian network, then we have the answer to the original SAT problem. Okay?
But converting the problem has to take far no time.
Absolutely, thank you. So the conversion cannot have an exponential growth, but yes. Okay, so here is the conversion. Given any CNF, what are we going to do? We will first generate a random variable for each variable in the CNF. So this is a CNF over u, v, w and y. So we are generating 4 random variables for u, v, w and y, taking 2 values, true, false. Next, we are going to create an intermediate node whose conditional probability table will be that it will represent OR. So it will have probability 1 if u is true, v is false, w is true, and probability 0 otherwise. It's a deterministic conditional probability table. Similarly, this one for this clause, this will have probability 1 if u is false, w is false, y is true. Then finally, we will have a conditional probability table for the AND of all these clauses. Now, we will assign a prior probability of half on each of these variables. So what are we saying? A priori, each variable can be true or false with equal probability. This variable will be true when it's OR, this will be OR, when this will be AND. Now then we ask the question, what is the probability that AND node is equal to true? Yeah, what's just the marginal probability, no conditional. If this probability is 0, what does it tell me? If this probability is greater than 0, what does it tell me? What does the probability tell me?
Exist awards.
Oh, it'll even give you a count. How many answers you got?
See, all of these are half probable. So each probability, each 1 over 2 to the power n probability here will give me exactly one satisfying assignment. If there's one satisfying assignment, it adds a probability of 1 over 2 to the n. So if you take this probability, multiply it by 2 to the n, what do we got? The number of assignments. So really, Bayesian networks is a much harder problem than satisfiability. Because in satisfiability, we just need to know whether it is satisfiable or unsatisfiable. That itself is NP complete. Now we are actually computing the number of solutions for a given SAT formula. So we are asking a much harder question. So therefore, Bayesian network inference is NP hard. In fact, it's in a complexity class called sharp P. Okay, for the people who understand theory, I don't. So it's actually sharp P complete. It can count the number of assignments to 3 SAT. That's it. So what we have shown so far is that exact inference is really hard, but we have an algorithm called variable elimination. We have special subclasses of Bayesian networks. We didn't get into that, but we can solve those in polynomial time. These Bayesian networks are incredibly powerful. They happen over and over in practice. We really want to solve them, but they are sharp P complete. As AI folks, we get excited that the problem is hard, because if the problem is polynomial, then the theoreticians will solve it. Problem is hard, it's harder than NP hard, even better. We want to come up with practical techniques to solve such hard problems. Of course, they won't be exact, which leads me to the next topic of the day, approximation based inference, approximate inference techniques. Questions before?
In the previous slide, how do you decide what needs to be called?
Based on the clause, we are given a SAT formula, we are converting it into.
V and W.
So this is an OR, which means that if U is true, it will be 0 probable if it will be 0 probable if U is false, V is true, and W is false, and it will be 1 probability for all other combinations. Basically, you will create a conditional probability table which is equivalent to the OR of the clause. So if U is true, probability will be 1. If V is false, probability will be 1. If W is true, probability will be 1. In the specific case that W is false, V is true, and U is false, then the probability will be 0. I had made a mistake there.
And you put the edges based